Hello and welcome to Physics Talk. Here we discuss various topics on physics and try to clear all your doubts. So come on, let's begin. Today we discuss the nuclear force and its features. The nucleus was discovered after the scattering experiment of Lord Rutherford in 1911, where energetic alpha particles were passed through thin gold foils, and the scattering of these alpha particles at various scattering angles were detected. The results of this experiment could only be explained if the features of gold nucleus is such that almost entire of its mass is concentrated at the center in an extremely small region and having positive charges, while negatively charged electrons orbit around this central entity called nucleus of the atom. The nuclei owe their positive charges to the particle proton, which has 1 unit of positive charge. Later on, one more particle, which was named as neutron and found to be electrically neutral, was also found to be present in the nucleus. This configuration of the nucleus immediately throws up a serious question. How is it that the positively charged protons are packed together in such a tiny space where they are actually supposed to break away because of the electrostatic repulsion between them? It is to be kept in mind that during that time, that is, at the time of discovery of the atomic nucleus, the only known forces of nature were electromagnetic and gravitational. None of these could explain the packing of positively charged particles in such a tiny space. The gravitational force, although attractive in nature, its value for such small masses is negligibly small in comparison to the electrostatic repulsion between the positively charged particles. Hence, the only way out was to propose an entirely new type of force named as nuclear force. While dealing with the fundamental forces of nature, this force is named as strong force. There are some fine differences between the strong force of the standard model and the nuclear force, but that is not part of our present discussion. Since an entirely new type of force came into the picture, of course, it was necessary to examine it thoroughly and draw information about its features. And that is the subject matter of our present discussion. The very first property of nuclear force obviously comes to our mind is that it must be much stronger than the electromagnetic force. It has to be much stronger than the electromagnetic force because overcoming the Coulomb repulsion between the positively charged particles, it keeps them tightly packed in such a small space. Although there is an attractive force also present in the system, that is the gravitational force, but it is many order of magnitude smaller than the electromagnetic force. Moreover, tiny masses of the particles make the gravitational force inside a nuclear system practically negligible. Hence, the only way out is to hypothesize an entirely new type of force, that is, nuclear force. The next task is to examine the range of the nuclear force. It is to be noted that the two forces known till then had ranges theoretically up to infinity. Now, coming to the nuclear force. Before it came into the picture, the atomic and molecular physics were well developed. All the phenomena connected with the atomic and molecular physics were successfully described in terms of electromagnetic force only. For example, the spectral lines. The experimentally determined values accurately tallied with the theoretical calculations performed using electromagnetic interactions only. Had there been any influence of nuclear force on the movement of orbital electrons, some disparity between the theoretical values and experimentally determined values must have been cropped up. Since no such discrepancy was detected, it is certain that nuclear force has no role to play on the movement of electrons. This phenomenon points to the fact that over the distance between the nucleus and the orbital electrons, the strength of the nuclear force dies down sufficiently to become practically nil. Here it is to be remembered that the atoms have their sizes in angstrom order, which is 10 to the power minus 10 meter. That means even at this extremely small distance of the order of 10 to the power minus 10 meter, the nuclear force has practically no effect. In other words, the range of nuclear force is extremely small. The next important property of the nuclear force is a consequence of its extreme short range. Because of this, inside a nucleus, the attractive nuclear force exerted by one particular nucleon is effective only over to the nucleons surrounding it. It does not have any influence over the rest of the particles in the nucleus. This is called the saturation of the nuclear force. This literally means the nuclear force exerted by one particular nucleon gets saturated very close to its point of origin. There is a consequence of this. Think of a big nucleus consisting of large number of nucleons. The entire system is held together such a way that every one member of it is connected to its nearest neighbors only and not others. Each of the neighbors in turn is connected to its own neighbors. The process takes place throughout the nuclear volume. Thus, as a whole, every particle finds itself in a resultant attractive potential. The situation here is drastically different from the atomic case. In an atom, there is a central body, that is the positively charged nucleus sitting at the center, and all the negatively charged electrons are kept bound to the system by this central body exerting its attractive Coulomb force. In contrast, inside the nucleus, there is no central body or agency that is responsible for the system to be bound. Here, every member of the assembly has its own contribution to the overall binding of the system. This is analogous to the drop of a liquid where the molecule where every molecule is attached to its nearest neighbors through van der Waals force. At this point, it is prudent to discuss the role of neutron in nuclear binding. In the periodic table, as we go from lighter elements to heavier elements, the atomic number, that is the number of proton, progressively increases by 1 for the next element. As we progress towards the heavier side, more and more number of protons are added to the nuclei of the respective element. In order to explain this in more detail, let us take one representative nucleus. If we look at the energetics, every proton in the assembly finds itself in an average electrostatic repulsive potential. In addition, the proton also experiences an attractive nuclear potential. The magnitude of the nuclear potential is much greater in comparison to the electrostatic potential, and hence the resultant potential is negative or attractive. Recall here again that the electromagnetic force is a long range force, whereas nuclear force has an extremely short range. With the increment of one more proton in the assembly, the average Coulomb potential experienced by every proton increases, whereas nuclear potential does not change because of saturation of the nuclear force. As a result, the magnitude of the resultant attractive potential decreases. In this way, as the proton number increases, the overall strength of the disruptive Coulomb force inside the nucleus increases, whereas at the same time it doesn't contribute to overall attractive nuclear potential, which remain unchanged because of the short range of the nuclear force. Thus, the magnitude of the resultant decreases and there is a net increase in the instability of the nucleus. In this way, with every increase in atomic number, the nuclei become more and more unstable. Here comes the important role of neutrons in countering this instability. Neutrons, being electrically neutral, do not contribute to the disruptive Coulomb potential. Rather, taking position in between the protons, they effectively reduce the Coulomb repulsion between the protons. Let us look at the energetics of this phenomenon. With the addition of one neutron, the effective Coulomb potential experienced by a proton decreases owing to the increased separation between the charged particles. This results in higher resultant attractive potential. Thus, with the addition of every new neutron, the nuclear stability increases. Now, let us look at the stability curve of the isotopes. The green curve gives the atomic number and the neutron number for the stable isotopes. As it can be seen, for the lighter elements, the number of protons and neutrons are nearly equal. Then from Z is equal to 20, that is calcium onwards, neutron numbers deviate more and more from the Z is equal to N line. This clearly indicates that with the increased atomic numbers, nuclei require more neutrons to counter the disruptive Coulomb force to remain stable. However, this mechanism of providing nuclear stability through neutron has a drawback. This disturbs the symmetry between the proton numbers and the neutron numbers, which is again a factor in nuclear stability. The meaning is that one extra neutron, while adds to the nuclear stability by reducing the Coulomb force, while at the same time it also contributes to the nuclear instability by disturbing the symmetry between the proton numbers and neutron numbers. This contribution towards instability becomes more prominent for heavier elements, where there is a large disparity between the proton numbers and the neutron numbers. Finally, at Z is equal to 83, which is Bismuth, the positive and negative contributions of neutrons towards nuclear stability becomes almost equal, and that is why no stable nucleus can be found heavier than bismuth. Here I have discussed some of the important features of the nuclear force. There are some other important features also that I shall discuss in next deliberations.